Okay, so this section of review is over radicals and rational exponents. And so we're really just going to focus on your basic radical properties today, and we'll do some of the trickier stuff tomorrow when I'm back. So the first two rules that I want to look at are the product rule and the quotient rule. Here is what these both say. So the product rule says that if I take the square root of a and I multiply that by the square root of b, then I can take the square root of the product together, the square root of a times b. That's also true in reverse. If I have the square root of a product, the square root of a times b, I can split it apart into two separate square roots by breaking apart the factors of that product. That product also extends to any nth root, but the index of the radicals must match. So like if it's a cube root of a times the cube root of b, you can do it. But if it's a cube root of a times the fifth root of b, you cannot. We have to do a little bit more work to combine those. You can, but it takes a lot more work. The quotient rule is very similar. I can either combine into one fraction with the square root, or I can take that square root and break it apart. And so these are helpful when we are trying to simplify expressions. So, for example, if I have the square root of 3x times the square root of 2y, I could rewrite that as the square root of 6xy. That can't be simplified any further, but we can combine that into one radical. Now, we also use this property to simplify radicals. So for example, if I have the square root of, say, 45, well, 45 is 9 times 5. And the reason that I would want to break it apart that way is because 9 is a perfect square. And I know what the square root of 9 is. That's going to evaluate out to a whole number. So I can simplify this to be 3 times the square root of 5. And that is how we are going to use this property to simplify radicals. With the quotient rule, we can do the same thing. I might have something like the square root of 4 ninths. Well, I don't know what the square root of 4 ninths is, but I do know what the square root of 4 and what the square root of 9 are. So that tells me that it's going to be 2/3. Okay. Similarly, you can combine them together. If I had something like the square root of 32 over the square root of 2, well, I could go ahead and divide those and get the square root of 16, which we know is 4. So that is kind of using that property in both directions there. So either one of those will work. The third property is the sum and difference of radicals, and that looks like this. So if I have like radicals, and that is the part that is really, really important here, you can only add or subtract like radicals. And if you recall the definition of like radicals, same index, cube root, fourth root, fifth root, same radicand. So in this case, they're both square roots, and the radicand of each one is n. So they have to match exactly, just like x squared and x squared are like terms. The square root of x and the square root of x are like terms. And so when you have that, you can just add or subtract the coefficients. So for example, let's say I had something like 3 square root 5 minus 2 square root 3 plus 4 square root 5. Well, the only two like radicals I have here are the square roots of 5. So I can combine those. 3 and 4 makes 7 square roots of 5, but the 2 root 3 doesn't have any like radicals, so it would stay the same. Okay? So let's look at a few examples where we're going to use these products. So using the product rule, the square root of 500, I mentioned yesterday, you need to know your perfect squares, and this is a perfect example of why. So let's put the perfect squares down the side of the page here. These are the perfect squares from 1 to 15, and so if you ever need this list, it's 1 squared, 2 squared, 3 squared, 4 squared, and so on. So what we're looking for to simplify this radical, the square root of 500, we are looking for the biggest perfect square that divides evenly into 500, and it is 100. So we can break this apart into the square root of 100 times the square root of 5. The perfect square is 100, so we get 10 square root 5 when we simplify that out, okay? If we look at number 2, first thing I'm going to do is go ahead and combine this into one radical. Since they're both square roots, I can multiply them straight across, and I get the square root of 18x squared. Now I need to simplify that. The square root of 18 has a perfect square factor of 9, and that's times the square root of 2. And then x squared is a perfect square, clearly because it says squared, but it is also true that any even power is a perfect square, x to the 4th, x to the 8th, anything like that. And so we can go ahead and count that also as a perfect square. So this is a perfect square, this is a perfect square. The square root of 9 is 3, the square root of x squared is x, and then we have a square root of 2 left over. Now just a reminder, from last year, if you have an nth root, like let's say I have the 4th root of x to the 14th. The way that you would figure this out is you would say, okay, how many times does 4 go into 14? Well, 4 goes into 14 evenly 3 times. So we would get out an x to the 3rd. It goes in 3 times to get to 12, which means I have 2 left over. So that means I would have an x squared left under the radical. And so that's just a refresher on how you would do your nth roots there if any of those turn up, okay? So example 3 then, using the quotient property, we're going to do the same thing. This fraction, I don't know what 25/16 reduces to, but I can do the square root of 25 and I can do the square root of 16 separately, and that will give us 5/4. On example 4, the first thing I would do is combine this into one square root and see if I can simplify that. So 150 divided by 2, that gives me 75. And x to the 3rd divided by x gives me x squared. Now 75 is 25 times 3. 25 is a perfect square, and x squared is a perfect square. So I get to bring both of those things out. The square root of 25 is 5. The square root of x squared is x. And then I have left over just the 3. That's the only thing that did not get to come out of the radical. So 5x times the square root of 3. Okay? Let's bring this down here. Look at adding and subtracting. Now, some of them are going to be really straightforward, like number 5 and number 6. So the first thing we need to do is scan to see if we have any like radicals. And I have a pair right here. That square root of 3 does not have a match. So I'm just going to combine the coefficients. The radical would stay the same. So 7 plus 5 gives me 12 square root 2 minus the square root of 3. That's as simplified as I can make that. Okay? Example 6, I have 1 square root of 5x minus 7 square root of 5x. Again, these match exactly, so we can go ahead and subtract, and I get negative 6 square root of 5x. Example 7 and 8, a little bit trickier because we're going to have to do some simplifying first to see if we have any like radicals. 7 square root of 3, that is already simplified all the way. But the square root of 12, I can think of that as 4 times 3, and 4 is a perfect square. So really we have 7 square root of 3 plus 2 square root of 3, and that'll come out to 9 square root of 3. So that does simplify down into one term. Number 8, we're going to have to simplify both of these. So 50 has a perfect square factor of 25. That's 25 times 2. And 32 has 16 times 2. Perfect square here, perfect square here. Now here's how you deal with these coefficients in front. I have a 4 in front here. So that means it's 4 times whatever I get. This is going to simplify to 5 square root 2x minus 6 times 4 square root 2x. And we're getting lucky here because our radicals match. But now we can go ahead and multiply the coefficients that are outside of the radical. So I have 20 square root 2x minus 24 square root 2x, which comes out to, whoops, I didn't mean to cross that out, sorry, negative 4 times the square root of 2x. Okay? And then the last thing that I want to talk about today are these simple rationalizing problems, okay? So in algebra, it's standard practice to rationalize the denominator. And what that means is, remember we talked about our number sets the other day. A square root of 3, for example, that is an irrational number. We prefer, in order to make sure that all of our answers look the same and that we have the easiest values to work with, we want the denominators to be rational numbers, not square roots. So the rule is you cannot have radicals in the denominator of a fraction. And the way that we fix that is to multiply by some form of 1 that is going to help to eliminate my square root. And the easiest way here for these problems is just to multiply by the square root that you have. So for example, 15 over the square root of 6, I'm going to multiply by the square root of 6 over the square root of 6. And so that gives me 15 root 6. I can't multiply those because the 15 is out and the 6 is in. But in the denominator, think about what this would give us. The square root of 6 times the square root of 6 would give us the square root of 36, which is just 6. Now make sure that you check these guys and see if you can reduce your fraction any further, which in this case we can, because 15 and 6 both share a factor of 3. So I can simplify that fraction to be 5 root 6 over 2. That's your most simplified value, and so that's what you would want to go with. Now on number 10, I could multiply by square root of 8 over square root of 8. It would absolutely work, and I could simplify. But I always like to say, think smarter, not harder. All I need is for the denominator there to become a perfect square. So right now I have the square root of 8, not a perfect square. But the closest perfect square to 8 would be 16. It would not be wrong to do square root of 8 over square root of 8, but it might be simpler to multiply by square root of 2 over square root of 2, because think about what that's going to give us. This is going to give us the square root of 16, which is 4. And then we can divide out the 12 divided by 4, and we get 3 root 2 for our final answer. You would have gotten the same thing, but you would have had to simplify that square root of 8 in the numerator. I'll show you off here to the side. You would get 12 square root of 8 over 8, but the square root of 8, remember this is 4 times 2, so you'd get 12 times 2 root 2 over 8. Well, 12 times 2 is 24, and then 24 divided by 8 would still give you 3 root 2 when all is said and done. So you always want to make sure that you get all your radicals simplified and all your fractions simplified. If they're not, my math lab is going to tell you that it is incorrect. Okay? So you have a math lab assignment to be working on here, and I will check back with you when I see you tomorrow.